So in chapter 8, we looked at basically thermochemistry, right? It's all about energy here in chemistry. So we defined whenever we're studying thermochemistry, we define two things: the system and the surroundings. The system is basically anything that we are studying. It could be a chemical system, a chemical reaction itself, and everything else is the surroundings. So the system that we're studying can exchange energy with the surroundings. So energy can go into the system from the surroundings, or energy can come out of the system into the surroundings. So you learned the different types of chemical reactions involving heat. There's endothermic and exothermic. So if energy is coming into the system, that would be endothermic. If energy is coming out of the system, that would be exothermic. All right. The energy lost by the system is always equal to the energy gained by the surroundings. Likewise, the energy gained by the system is equivalent to the energy lost by the surroundings. And so the total change in energy of a chemical system is equivalent to the energy of the products minus the energy of the reactants. So you take the difference in the energies between the products and the reactants, and what you get is the total energy change of the system. Again, the system could be a chemical reaction. A positive change in energy, right, meaning it's greater than zero, a positive change in energy means energy was absorbed by the system, that energy went into the system, energy was added into the system. On the other hand, if the total change in energy is negative, less than zero, it means that energy was released by the system. So energy was subtracted from the system because it left the system. Another concept that we looked at in chapter 8 is heat and also work, right? Because the system can exchange energy with the surroundings via heat and work. And they have these symbols. Heat is little q, work is little w. We can quantify the amount of heat that was exchanged between, or the amount of energy that was exchanged between the system and the surroundings by using this equation right here. So the change in energy is equivalent to heat and work, heat plus work. Here's an important sign convention here that you should be aware of. If heat was positive, that means that the system absorbed heat. So if heat is coming into the system, like you're heating um, the chemical reaction or something, that means that the chemical reaction is absorbing heat and you would give it a positive value. On the other hand, if the system is the one that's releasing heat into the surroundings, you would give it a negative value, a negative sign. For work, if the system is the one that's receiving work, right? If the system is the one that's receiving work, then it gets added into the system and that's going to be a positive value. Otherwise, if the system is the one that's performing work, which requires energy, work would have a negative sign. Because again, it's being subtracted from the system if the system is the one performing work. All right, let's take a look at an example here. We have the combustion of butane gas releases 40 kilojoules of heat and performs 62 kilojoules of work. What is the change in the energy of the system? So, according to this statement, the system, the chemical reaction here, the combustion of butane, releases 40 kilojoules of heat. So because the system released heat, it's being subtracted from the system. So you give it a negative sign, negative 40 kilojoules. All right. And because the system, the chemical reaction here, is the one that's performing work, it requires energy, right, in order to perform work. And so you would give this sign a negative sign as well. So that would be W equals negative 62 kilojoules. So now we can use this equation right here to calculate delta E, the change in the energy of the system. So plug the numbers in, negative 40 plus negative 62, and we get negative 102 kilojoules of energy. So again, the negative sign here tells you that 102 kilojoules of energy was released by the system. The negative sign tells you it was released by the system. Second to the last concept here is quantifying heat. How do we quantify the heat generated or absorbed by a system? So let's take a look. We can quantify heat by using this equation right here. Q equals MCAT, right? Mass times the specific heat capacity times the change in temperature. And the change in temperature can be calculated by simply taking the difference between final temperature and initial temperature. One thing that you might want to remember is the specific heat capacity of water, which is 4.184 joules per gram degree Celsius. Here's an example. How many joules of heat are required to raise the temperature of water with a mass of 550 grams by 20 degrees Celsius? Okay, so here you can see that the specific heat capacity of water was not provided here. You just have to remember that. It's 4.184 joules per gram degree Celsius. So it's asking for the amount of heat required to raise the temperature of water. We can use this equation shown here. Q equals the mass of water, which is 550 grams, multiplied by the specific heat capacity of water, multiplied by the change in temperature. Change in temperature would be 20 degrees Celsius because you're raising the temperature of water by 20 degrees Celsius. So that's already the change in temperature. All right, plug this into the calculator and we get 46,024 joules, which can be rounded to 46,000 joules with proper number of significant digits. And the last concept here is determining specific heat capacity via calorimetry. So here's a coffee cup calorimeter where you have two nested styrofoam cups with a lid, and inside of it you have the solvent, which is typically water, or a chemical reaction inside, or a piece of metal. You have a thermometer and a stirring rod. So how do we determine, let's say, the specific heat capacity of a metal via calorimetry? So you can always set up your equation like this, where the heat ab absorbed by the water is equal to the heat released by the metal. So the negative sign tells you heat is being released. All right, so we know what Q is equal to. It's mass times specific heat capacity times the change in temperature. So Q water is equal to the mass of the water times the specific heat capacity of the water times the change in temperature of the water. Likewise, Q metal here is equal to the mass of the metal times the specific heat capacity of the metal times the change in temperature of the metal. And so we can calculate the specific heat capacity of the metal by simply isolating this by itself. And so we can divide both sides by negative m delta T for the metal, as shown here. So this is the isolated variable here. So this is the formula that you can use to determine the specific heat capacity of a metal. So you don't actually have to derive this equation here, but you should be able to come up with this knowing algebra. All right, so let's take a look at this one last example here. The initial temperature of the water with a mass of 110.5 grams in the cup, the cup calorimeter, was 25 degrees Celsius. A piece of gold metal with a mass of 52 grams with an initial temperature of 100 degrees Celsius was submerged into the water in the calorimeter. The final temperature reached 26.1 degrees Celsius. Calculate the specific heat capacity of the gold metal using the information shown here. So we know the equation for specific heat capacity. So all we have to do now is plug in the numbers. So we have the mass of the water, we have the initial temperature of the water, and the final temperature of the water. We also know the mass of the metal, the initial temperature of the metal, and the final temperature of the metal, which is the same as the final temperature of the water. All we have to do now is plug it into this equation, this formula shown here. So we have negative mass of the water times the specific heat capacity of the water times the change in temperature of the water, which is final minus initial. And then we're going to divide this by the mass of the metal times the change in temperature of the metal. Again, final temperature minus initial temperature of the gold metal. Plug this into the calculator and we get 0.132 joules per gram degree Celsius.